The mute button was hidden.
Hidden. Okay.
Okay, so good afternoon. Welcome to this presentation on chiplet integration technologies. My name is Elko Bergman. I'm with ASC Group. And ASC has been participating in the ODSA for about a year. And during this time, we've identified opportunities for us to collaborate with and add value to the ODSA effort. Today, I'd like to briefly introduce our technology and service offering for enabling the heterogeneous integration of chiplet-based solutions. And I'll share with you also what's driving our interest in participating in the ODSA project and how we believe we can support the development of this chiplet ecosystem. So integration and miniaturization has been a way of life for the semiconductor and electronics industry since its inception, really. Increased functionality, higher performance, reduced power consumption to continue to be at the forefront of product development as we move from one generation to the next. On the chip side, up until the past 2 years, the path has been to leverage Moore's Law and an SoC integration, and simply by adding more and more functionality to a single device. The system side, of course, has benefited from this, allowing more powerful products in shrinking form factors, from mainframe to laptop, from mobile to wearable. However, starting with 60 nanometer and below, a new trend has emerged as a result of the increase in costs associated with advanced silicon, namely die partitioning and chiplets, resulting in a new type of integration requirement, specifically heterogeneous packaging-based integration. ASC recognizes the industry's drive towards die partitioning and the growing need for the integration of heterogeneous silicon into virtual SoCs. This trend is driven by a variety of factors, including silicon and cost and yield improvement, IP reuse, node and performance optimization, separation of digital and analog functionality, and increased performance and bandwidth, particularly as the IC developers continue to move to larger die sizes and more advanced process nodes. These integration drivers, these factors, can also be separated into 3 core categories, specifically silicon integration, power integration, and optical integration. So to address this industry direction, we offer a full range of advanced interconnect solutions for silicon integration, starting with PCB substrate-based SiP modules for wearables, IoTs, and other consumer applications. And then moving towards the right with increasingly higher density interconnect solutions, including flip chip MCMs to support multi-die integration such as SoC with SerDes, high density fan-out interconnect for large die partitioning and HBM integration, and all the way up to silicon-based 2.5D and 3D integration platforms, leveraging sub-micron line and space routing capabilities. Needless to say, all of these heterogeneously integrated package solutions require significant design and simulation support that would normally occur during the SoC design process. It's here where ASC sees the potential benefits of the standard interface development that the ODSA has undertaken. And in the next several slides, I'll focus specifically on the technologies highlighted in the middle by the red box. So the first is flip chip MCM. So as I mentioned here, we're using substrate-based interconnect. So you're typically looking at greater than 10 micron line in space and interconnect distances that could be at least 2 or 3 millimeters. Generally, you're looking at core layers with build-up layers, so 16, 18 layer totals, and your die-to-die interconnect densities are in the hundreds to thousands. In terms of packages, we do see package sizes growing pretty dramatically. We've qualified up to about 80 by 80 and have solutions up to 120 by 120 in development. So this, I think this is an example that was shown earlier too by Michael. You know, it really supports die partitioning and enables the use of IP dies such as SerDes, et cetera, for interfacing with your chips. High density fan out, for ASC we call it Focus, but now we're using high density lithography based RDL. So we deposit an interconnect layer on a reconstituted wafer with different partition die or chiplets. And now we can go down to 2-micron line in space. We have routing layers up to about 4 layers. And then once the die is reconstituted with these interconnect layers, then you can flip chip that onto a traditional substrate. So my apologies. If you look in the lower right corner, you see a good example. You see the 2 devices separated by a little bit of molding compound. You see the die level RDL layers, the C4 bumps, and then the interconnect onto the package substrate layers at the bottom. And this gets you routing densities that are in the thousands to 10,000s from die to die interconnect level. The high density RDL can also be used as a TSV alternative. There's 2 ways to do these RDLs. One is what's called chip first, where we place the die and reconstitute the wafer first and plate the RDL layers directly to the die surfaces. The second is where we form the RDL layers first on a carrier layer and then flip chip attach the dies to that RDL layer. And this is what would be required if you were trying to integrate, for example, high bandwidth memories, which come with solder bumps already on them. And then, of course, 2.5D, here you have the traditional silicon-based interconnect solution. So now your sub-micron line in space, typically in the 0.4 range. Again, you have multiple layers, and now you can get extremely high die-to-die interconnects. This is certainly what enabled the interconnect of high bandwidth memory stacks in a lot of the initial applications. So we acknowledge the significant thrust towards heterogeneously integrated solutions, and we've been making significant investments in package technology development and advanced manufacturing tools to support this direction. One of the keys to success in achieving this widespread adoption is the development of the enablement of a complete ecosystem across the value chain in order to simplify the design and the integration process. The ODSA's effort in developing physical and logical interface standards is a significant step towards that objective. And as the industry moves to partition virtual SoCs, a portion of the interconnect design complexity that was previously dealt with at the chip level has now been moved into the package. So to avoid complex custom and extended design and simulation cycles, there's a significant need for the development of interface layout standards, design rules, reference designs, and guidelines to facilitate this process. The ODSA's effort in the development of these interfaces needs to be extended and optimized for various types of package level integration technologies, including substrates, high density RDL, and silicon interposers. And this will require the involvement and support of the EDA community in order to enable the true co-design and verification of these heterogeneously integrated structures. And then lastly, to support the manufacture of these highly integrated and highly interconnected structures, there's also a growing need for advanced metrology and inspection tools to monitor and control the assembly processes. With the increasing value of the devices being integrated, quality, yield, and reliability are paramount. And we're working closely with the tool suppliers on the definition and development of these tools and encourage the participation of ODSA members. Thank you.
Hey, thank you, Elko. Really appreciate the time.